Welcome to this explainer. I am incredibly pumped you're joining me today because we're embarking on a serious journey. We are going to completely transform how you tackle your Cambridge computer science exams. Today, we're mastering the mechanics of answering questions specifically on binary addition and overflow. Now, whether you're sitting the 0417, the 0478, the 2210, or the 9618 syllabus, you probably already know that the exam paper can feel a bit like a wasteland of tricky questions, just waiting to trap you and steal your marks. But today, we are going to navigate that wasteland together and claim your grade treasure. I want you to picture two students that examiners see on paper every single year. First, there's Alex. Alex is the kind of student who overloads the exam paper with raw computer science facts. When asked a straightforward question about binary overflow, Alex completely ignores any context or analysis and just writes out every single rule of binary addition, dumping a massive, confusing paragraph of ones and zeros onto the page. The result? A brutal sea of red pen from the examiner. Then, on the other end of the spectrum, we have Sam. Sam rushes. Sam sees the word overflow, completely panics, and just scribbles down "the computer crashes because the number is too big," completely missing the actual command word requirements of the question. And again, more red pen. The tragic thing is, both of these students studied hard. They knew what binary was, but both of them lost massive marks because they lacked a strategy. Well, today, we are going to change that for you.
We've got a tight roadmap for this explainer. We'll be hitting the real binary problem, looking at 3 layers of understanding, breaking down description versus explanation, doing a rapid method review, securing your attention, and finishing with a powerful 4-question self-check.
Let's jump right into Section 1, the real binary problem. To really get started, we have to recognize a fundamental truth. Learning binary concepts as just an isolated vocabulary list, like a set of flashcards you just memorize, is an absolute, guaranteed way to drop marks in a Cambridge exam. This is exactly the trap our student Alex fell into. Alex treated binary addition and overflow like a simple spelling test. You know the drill. 1 + 1 is 0, carry the 1. Overflow is when the result exceeds the allocated memory. Boom. Memorized, right? But here's the real underlying binary problem. Examiners don't just want to know if you can recite a textbook definition. They are deliberately testing your ability to understand a connected, functioning computer science structure. When you just learn an isolated definition, you build absolutely no mental framework to apply it when the exam board throws a complicated curveball scenario at you. You have to start with the digital problem itself. Why on earth was this concept invented in the first place? Transferring this dry, theoretical math to the real world is what actually matters. Think about the systems around you. Mobile phones, massive databases, banking systems, and advanced robotics. If a binary overflow error happens in a banking system, it's not just a math glitch. Someone's bank account balance might suddenly drop to 0, or mistakenly jump to millions, simply because the physical hardware couldn't handle the extra bit generated by a single binary addition. Or consider robotics. In a manufacturing plant, an overflow error could cause a massive mechanical arm to swing wildly out of control instead of stopping at its safely designated limit, endangering lives. When you repeatedly connect the abstract theoretical concept of binary addition to these incredibly high-stakes real-world technologies, you aren't just memorizing a label anymore. You are deeply understanding the fundamental reason the concept even exists, which is exactly what the examiner is looking for.
So the absolutely crucial takeaway here is to always begin your study sessions by answering this specific question, rather than just jumping straight into the binary terminology. Ask yourself right off the bat, what is the practical consequence of this? If you can successfully explain the real-world consequence of an overflow error for a user, like their secure online activity completely crashing or an international organization losing critical financial data, you have immediately elevated your exam answer from a basic low-tier grade to a top-tier grade. You are explicitly showing the examiner that you don't just know the math, you understand the actual stakes of the technology.
Moving right along to Section 2, 3 layers of understanding.
Remember our second student, Sam, the one who rushes and completely misses the command words? Sam is permanently stuck in the lower layers of understanding. The Cambridge assessment objectives for computer science are incredibly specific, almost ruthless. They use distinct command words like state, describe, explain, and evaluate. If you do not directly tailor your knowledge to the exact requirement of that specific command word, you will bleed marks, no matter how much you know. Students so often trick themselves into thinking they know a topic when they are only at layer 1 or 2, until they are suddenly forced to express it in that critical third layer under severe ticking clock exam pressure. Let's break these down. Layer 1 is just everyday language. You might sit there and say, well, overflow is when the computer runs out of space for numbers. Okay, fine. That gives you a basic conversational grasp of the idea, but you won't get marks for it. Layer 2 steps it up by bringing in technical vocabulary. You might write, overflow occurs when the result of a binary addition requires more bits than the CPU register can physically store. Okay, much better, right? That demonstrates a solid academic understanding. But layer 3, the exam explanation, is where the real magic happens and where the top grades live. This is where you deploy the Peel framework. You make your point, you provide evidence using the very specific binary values given to you in the exam question, you explain the mechanical process of that extra bit physically falling off the register, and then you link it all back to the specific system crashing in the provided scenario. This layer 3 approach is deliberately shaped for time pressure, and it is the only way to guarantee a high-scoring answer. Before we continue, subscribe to our YouTube channel Ace the Exams at aceexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's head into Section 3, Description versus Explanation. Building a top-tier answer requires separating two very specific, very distinct skills in your mind. I want you to imagine Alex and Sam sitting in the exam hall right now. Their papers are covered in those brutal red marks. We're going to mathematically wipe that red pen away and replace it with green check marks right now. Here is the rule. If you just describe a concept, your answer is fundamentally incomplete. But on the flip side, jumping straight into an explanation without actually naming the concept first leaves the examiner totally confused. You absolutely must do both. Let's look at a shallow answer. Alex wrote, binary overflow is when an extra bit is generated. That's the description. It tells the examiner what the thing is. It honestly feels like a safe answer to write, but it's incredibly shallow. Best case scenario, it gets maybe one single mark. But for a deep, mark-grabbing explanation, Sam needs to step up and write something like, when two 8-bit numbers are added together and the sum mathematically requires a 9th bit, the physical CPU register cannot hold it. This extra bit is dropped entirely, meaning the resulting value stored is completely incorrect, which directly causes logical errors and crashes in the software. Do you see the massive difference there? The second answer tells how it works and exactly why it matters. It beautifully connects the dry theory to a concrete reality. I want you to try this mental exercise right now. I'm putting 60 seconds on a virtual clock in your head. If you had to rewrite a basic, flimsy description of binary addition into a full, robust explanation, how would you structure it? Think deeply about employing that Peel framework we talked about. Point. The register is locked at 8 bits. Evidence. The mathematical addition creates a 9th bit. Explanation. The hardware literally cannot store that extra bit, so it's discarded. Link. The running program receives corrupted data as a result. That framework right there is your ultimate computer science success blueprint.
Now let's talk about boundaries, because these boundaries absolutely control the quality of your whole answer. A huge, devastating loss of marks happens in Cambridge exams when candidates recognize a familiar vocabulary word in the prompt, panic, and end up answering a completely different question than the one being asked. Examiners actually love to test if you know the strict boundaries of a concept. Just like you need to understand that binary overflow is specifically a hardware register limitation and not just some random software bug, you have to precisely know the difference between other critical contrasts. Things like memory versus storage, data versus information, or a compiler versus an interpreter. If a question specifically asks you how an overflow error affects short-term memory and your brain panics and starts writing an essay about long-term hard drive storage, you will get 0 marks, period. You successfully recognized a familiar digital concept, but you answered the completely wrong question. Precision is everything in these exams. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at ACEXAMS IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @ACEXAMS IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's transition into Section 4, the Rapid Method Review.
Now we are reaching the absolute core of our exam strategy, a disciplined, highly technical path for approaching literally any binary addition or overflow question they throw at you. To avoid writing a jumbled, panicked mess, you desperately need a precise system for the exam hall. When you first look at a complex exam question, your brain is naturally going to want to dump every single computer science fact you've ever learned straight onto the page. You're going to feel the panic setting in, you'll hear the clock ticking loudly in the background, and you'll just start frantically writing. That is exactly what our friend Alex does. We have to completely stop that impulse. We need a rigid structure that forces your brain to organize the information logically, step by step, ensuring you systematically hit every single point on the examiner's hidden mark scheme. This 4-step sequence is incredibly powerful, particularly because so many computer science topics are fundamentally process-based and demand a strictly logical order of operations. You cannot skip steps. Step 1. Identify the demand. Read the prompt carefully. Is the command word state, describe, or explain? That dictates your entire approach. Step 2, classify the concept. You look at the scenario and say, okay, this is specifically about an 8-bit register overflow issue. Step 3, explain the sequence step by step. Don't rush to the end. First, the mathematical addition happens. Then, the 9th bit is generated. Then, the physical hardware cannot accommodate it, so the bit is lost. Then, the remaining data is corrupted. Step 4, connect it back. This is where your PEL link comes in to save the day. Connect that corrupted data directly back to the real-world scenario given in the question. If you panic and jump forwards and backwards in the sequence, the examiner completely loses the thread of your logic, and you lose those precious marks. Always, always remember that generic, copy-pasted textbook responses rarely gain full marks. If the exam paper gives you a highly specific context, let's say an industrial monitoring system, your entire explanation must stay locked tightly inside that specific context. We are going to enter the interactive workshop phase of this explainer right now. Challenge number 1, the data scan. I want you to imagine a complex computer science data table right in front of you, showing live sensor readings in an industrial heating system. I'm starting a 60-second visual countdown timer in your head right now. The data shows binary inputs from a heat sensor adding up, getting higher and higher, and suddenly, inexplicably, the output value drops completely back to 0. What just happened? If you use our 4-step sequence, you scan the data, you remain calm, and you see the core trend. The numbers got too mathematically high and reset. Why? Binary overflow. But if you just write a generic lazy answer about computers crashing, you fail the question. You must lock into the context. You write, the binary addition of the continuous heat sensor data exceeded the capacity of the 8-bit register, causing a catastrophic overflow, which means the industrial system will incorrectly read the boiling temperature as 0, potentially causing a critical overheating failure in the facility. Boom. That is exactly how you get maximum marks.
Section 5. Securing retention and transfer.
Let's explore how a really high-quality revision cycle actually locks all of this complex information securely into your long-term memory. We've talked a lot about how to write the answers, but how do we ensure you actually remember these strategies weeks from now when we were sitting in that freezing cold exam hall? I'll tell you right now, the secret isn't just mindlessly reading your highlighted notes over and over again. The actual secret is layered repetition, deliberately forcing your brain to transfer the knowledge to new, uncomfortable scenarios. This layered repetition is vital because surface features, like a familiar device name or a recognizable symbol in a question, can easily distract your brain from the actual underlying mechanical process. Pass 1 of revision is where you firmly secure the basic definition. Pass 2 is rehearsing the step-by-step explanation until it's muscle memory. But Pass 3 is where true adaptability is forced. Let's do Challenge 2 of our interactive workshop, Find the Flaw. I'm going to read a flawed sample paragraph, and you have exactly 60 seconds to find the specific sentence that is losing marks. Ready? Listen closely. Binary overflow happens when a calculated number is too big. This means a 9th bit is created in an 8-bit system. The extra bit is saved on the hard drive for later retrieval. This causes the active program to crash. Okay, did you spot the fatal flaw? It's the third sentence. The extra bit is saved on the hard drive. No, it absolutely isn't. The hardware register drops it completely into the void. It is gone. That is a massive error in understanding the underlying mechanism. If you don't practice Pass 3 and force your brain to adapt to different scenarios, your brain will literally invent logical-sounding but entirely incorrect facts under the intense pressure of the exam.
Studying error-aware notes that explicitly highlight these specific common mistakes is far more useful than just reading a boring list of correct facts. This brings us straight to Challenge 3, speed writing. You have exactly 30 seconds on the clock. I want you to mentally write one perfect PEL paragraph on why error awareness is critical for an exam answer, specifically about binary overflow. Go. Point. Error awareness directly prevents mark loss. Evidence. Stating a vague phrase like overflow crashes computers without any mechanical justification gains absolutely 0 marks from the examiner. Explanation. The Cambridge mark schemes strictly require the mechanical why, meaning you must state that the 9th bit is physically dropped from the register as there is no space. Link. Therefore, intentionally focusing on these common generic mistakes during your revision ensures your final answers meet the exact rigorous criteria of the command words. Time's up. If you can structure your thoughts like that, you are practically unstoppable. You have to deeply know what a terrible answer looks like in order to consistently craft a perfect one.
Let's bring it all together in Section 6, the 4-question self-check.
We are going to conclude this explainer with the ultimate practical self-check to test if your knowledge is genuinely, truly ready for the examination room. This is your final bulletproof system. First, you must be able to clearly define the device, the concept, or the process using precise academic terminology.
For binary overflow, it is strictly a hardware limitation where the result of an arithmetic operation mathematically requires more bits than the available CPU register can physically accommodate. This is your rock-solid foundation. If you cannot answer "what is it" using that level of technical vocabulary, you are honestly not ready for the exam. It means you are still stuck in Layer 1 everyday language and you need to go back and review.
Second, you must be able to logically sequence the exact mechanism without jumping forwards and backwards in the process. This is the crucial step-by-step sequence we discussed. When two maximum binary values are added together, a carry bit is generated at the most significant bit position. If there is literally nowhere for this carry bit to go, for example, it's a 9th bit trying to squeeze into an 8-bit system, the bit is entirely discarded and the remaining 8 bits now represent a completely incorrect, much smaller numerical value. That is exactly how it works, explained cleanly, chronologically, and logically.
Third, you have to apply it to a real-world scenario, shifting it from abstract whiteboard theory to a practical, tangible tool. We talked about industrial heat sensors earlier, which is a great example, but it could just as easily be a digital speedometer in a smart car, a high-score counter in an arcade video game, or a transaction calculator in a busy retail environment. You must prove to the Cambridge examiner that you deeply understand this concept. It doesn't just exist in a textbook. It actively impacts physical, functioning systems in the real world.
And finally, question 4. You must justify its use by providing a crystal clear advantage or disadvantage tied directly to that specific scenario. In the case of binary overflow, it's almost always going to be a severe disadvantage or a critical error state. You would explain that this limitation is significantly worse than having a system with a larger, perhaps 16-bit or 32-bit register, or a system with robust software error handling protocols, because an unhandled hardware overflow directly leads to corrupted data, wildly unpredicted system behavior, and potential catastrophic failures in highly secure environments. You are providing the ultimate top-tier justification.
I want you to look at this idea. If a concept can be paraphrased accurately, it is far more likely to survive in an exam hall. This quote brilliantly illustrates that true exam mastery isn't about perfectly memorized robotic wording. It's about completely owning the underlying reasoning. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Think about that for a second. You can jump from a C to an A simply by changing how you structure your thoughts and your answers. But this massive transformation only happens if you put in the reps. You have to internalize this reasoning so deeply that no matter what crazy out-of-the-box scenario Cambridge throws at you, your brain automatically defaults to the Peel framework and the rapid method review. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
Think about that question closely. If I handed you a past paper right this second, could you do it? Because once you can easily, confidently answer those 4 self-check questions aloud for any topic, you've officially moved from passive learning to true, undeniable exam mastery. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. But I'll leave you with one final provocative thought to chew on. If a simple 8-bit overflow can cause a localized system failure in a heat sensor, what exactly happens when an unpredicted 64-bit overflow occurs in a globally connected, international banking database? The stakes, my friends, only get higher from here. Keep reviewing your notes, relentlessly apply this structure, and I will see you in the next explainer.